All right, so of course, let me know if there's any issues if you can't see anything. So my name is Darren, and I am a physics major, and the title of this project is Morphology of Gas-Rich Radio Galaxies. So to start this all off, let me see. So astronomers have been studying many different types of galaxies for over a century, from bars, spirals, dwarfs, ellipticals, so on and so forth. But one unifying characteristic of all of these, or most of, if not all of these galaxies, is the black hole at the center of these galaxies. And what we're studying in this project is the area around that black hole, which contains multiple structures, which is called the active galactic nucleus. And this is defined as the central region of the galaxy containing the supermassive black hole and its surrounding structures. So in this diagram on the right, you can see it's sort of the classical picture of an active galactic nucleus. I'll refer to it as a AGN from this point. So looking at the anatomy, we can see a sort of toroidal or donut-shaped gas cloud surrounding the accretion disk, which is fueling the jets of the black hole, which are ejecting in the radio spectrum. And we can see sort of broader emission lines measured near the structures at the center of the AGN. So there's different, it's emitting throughout the electromagnetic spectrum. And so looking at the evolution of galaxies, we'll notice that there's a close correlation between the properties of the AGN and their host galaxies. So like the evolution and the nature of the galaxies. Recently, however, it's been discovered that there are two main types of AGN that reside in two unique types of galaxies. So this is sort of the classical picture, but we'll see another picture. All right, so the first one is what is known as the radiative mode Agn, and this is what you see. This is sort of the more classical picture. It resides in younger galaxies with blue-green hues. They're typically spirals. They have emission across the spectrum in UV, optical, X-ray, and radio waves. They're fueled by cold gas accretion, either via mergers with other galaxies or like surrounding neighborhood gas, and they have a high accretion rate. So this is sort of the classical picture of an AGN with these younger spiral galaxies. But recently it's been discovered that we can have active galactic nuclei within a more elliptical, older galaxies, and we call these jet mode AGN because they typically have these really powerful radio jets that emit out of both sides of the poles. So these are mostly radio emissions. They're fueled by hot gas from the stellar halo surrounding the galaxy. They have a low accretion rate. These galaxies typically contain old stars, and so that means they're redder galaxies. And these are elliptical galaxies because they've usually gone through some turmoil that has sort of churned up the galaxy, made them less of an elliptical, or made them less of a disc shape and more into like a bulgy sort of sphere. All right, so that introduces the question that we now find. So despite this classification, there is actually a small fraction of jet mode AGN within actively star-forming galaxies. So that means that there's this new type of AGN with these powerful jets that are found in the younger galaxies, and this is typically not the case. So the goal of this project is to try to determine the cause of this. All right, so why did this happen? So sort of a hint that we found is that with older data from the SDSS survey, we find roughly 30% merger rate in star-forming jet mode galaxies with only 5% mergers in non-star forming jet mode galaxies. So there's a high rate of mergers, or a higher 30% rate of mergers within these weird new type of galaxies that sort of break the boundaries. So we sort of think that this cause is because of mergers. So that is sort of the goal of this project. So more discreetly, we'll say the purpose is to determine the morphology of the host galaxies of the star-forming jet mode AGN and find the fraction of these sources that have features related to a merging event. And also, in addition to this, we're using newer surveys as opposed to older surveys. So we're trying to make a more robust understanding of the morphology of star-forming jet mode galaxies with deeper images. All right, so The methods we'll use are reducing the images, so take the science image and sort of resolve it better and make it easier to do science on. We'll do an image quality comparison with older surveys. We'll fit the images and subtract major features such as the bulge and disk to reveal detailed inner structures. And we'll analyze these substructures to create a catalog of the newer galaxies so we can determine if mergers are the cause of these weird, unique galaxies. All right, so the first, looking at the image depth, in order to provide a more robust understanding of jet mode radio galaxies, it's important to obtain deeper imaging. So you can sort of see in this image on the bottom right, the top 4 images are from older data and the lower 4 are from newer data. So it's easy to see how these deeper images will be able to reveal more sort of the substructures of these galaxies. All right, and the data in this project came from these surveys, and these gave deeper images than previously used SDSS. So SDSS is the older data, and these 5 newer surveys are newer data. So let's see. So first we need to calibrate our images, which is sort of a standard data reduction process. So to get from the raw image from the telescope to a science image that we can actually analyze. So first we need to subtract and trim the overscan region. So basically you can see there's this perimeter around the left side picture, and we need to subtract that off. Next, we subtract the master bias. So all exposures have sort of an offset or an array of pixel variations which compose the master bias, and this needs to be subtracted off. So it's basically like variations in the pixels that we need to be smoothed out. We divide the master flat. This is sort of a similar process. We don't really need to go too much into detail on how these all work. Finally, removing cosmic rays. Small cosmic rays can hit the telescope and cause these weird perturbations in the pixels, and those need to be removed. So once we've done this process, we can get from the left image, which is pretty blurry, to the right image, which has a lot of usable information. All right, so let's see. So source extraction. So this is basically getting a catalog of data from the image itself. So using a software package known as Sextractor, sort of a combination of source extractor, right? So we produced a catalog of sources associated with each image, including properties of the sources, such as magnitude, RE index, which is basically sort of the angular position in the sky, and the flux error. Along with a package called SCAMP, which compares the data with astrometric data from old SDSS data, we have a more accurate picture of the region of interest. So this is just basically cataloging the data, making sure that the source or the galaxy that we're looking at is like what we're trying to look at. Okay, so next, this is sort of like a way to get a better picture of what we're looking at. So co-edition image assembly. So several images of each region were taken at different times and assembled using a program called SWARP. This was done in order to reduce the negative effects of CCD artifacts, pixel saturation from overexposure, and other irregularities that might hinder the image quality. So basically, long story short, you take different pictures of the same region in space, but like slightly shifted around, and then you add them all up to a combined picture. So this will basically subtract any weird pixel variations that we get off, so we have an even cleaner picture. All right, so in order to find the image depth and confirm that we have deeper images for better analysis, we look at the completeness limits of the surveys. So completeness is sort of like a statistical term, which means we have a reasonable fraction of galaxies that we're looking at that are usable for our data. So completeness is a ratio of the detected sources counts to the total source counts at a given magnitude. So there might be, say you have 100 sources, but you can only see 80 of them, then you would have an 80% completeness. Okay. At lower brightnesses, the telescope will detect a lower fraction of the total sources. So this means you might see 50, say, stars per 100 stars that are actually there. So completeness limit is the magnitude at which the completeness passes a specified value, and magnitude is just this fancy astronomy term which means brightness. So say you have a magnitude of 5 and you see 80 out of 100 stars in the sky, that means you have an 80% completeness at a completeness limit of 5. And I used a software called SkyMaker to simulate these dim sources that we can't actually detect, and made these completeness limit plots to sort of determine what the completeness is of each of our different images that we're using. So this is just more cleaning the data, making sure everything is up to shape so we can analyze it better. So surveys with similar completeness limits will ensure that we can make a fair comparison between the morphologies of the galaxies within each survey. So we take all these completeness limits and then we compare them and we make sure that our data is usable. And this happened to turned out to be the case. So now to sort of the main part of the project. So the final step in actually analyzing these galaxies is coming up with a routine that subtracts major features such as like the bulge or large gas clouds out of the galaxy in order to look at the detailed inner substructures that might tell us more about the morphology of the galaxy. So the method that we go about doing this is galaxy fitting. And so the first step is we produce a 2D function fit to a galaxy using a software called InFit. So that's the center picture. That's sort of just this white circle in the black background. And we subtract this image from the science image on the left. And I did this using MATLAB. And then finally, it reveals sort of this weird, interesting little spiral that kind of tells us sort of what's going on with the morphology of the galaxies. It helps us determine more about the merger history, or like if this galaxy is a product of mergers or if it's not. So here's a couple more examples. You see the image on the left and they fit in the middle, then the subtraction. So we did this about 24 different candidate galaxies, and we made a full sort of catalog of these galaxies to look at their substructures and merger history. And we determined that there was a fair amount of these that were results of mergers. So we now have a more robust model of the morphology of the host galaxies of star-forming jet mode AGN. So before there hasn't really been studies on this, and it's all been with old SDSS data that with not very good resolution. So we've done this with a higher resolution, and we've determined that mergers can in fact be the cause of these weird types of AGN within the newer galaxies. So basically you have a elliptical old red dead galaxy with a jet mode AGN, and it's been merged with another galaxy that has sort of churned the galaxies to make it look like a star forming galaxy. All right, so we've also demonstrated the value of taking deeper images. So using the newer images as opposed to the older images has produced better data. And in future projects, we hope to take even more images of these galaxies at possibly deeper magnitudes in order to further the confirmation of our results. And we want to provide more statistical data for these galaxies. So just build up a more robust sort of data set so that we can look at these galaxies and determine for certain that the mergers are the cause of these star-forming jet mode AGN. So thank you for watching, and thank you to these people for helping me with the project.
All right, great job. So actually, Darren, we're going to ask you to turn your recording off now. I'm sorry, I forgot we weren't supposed to record the questions. So yeah, awesome job, and we'll let you turn that off, and then we'll take some questions.